Okay, good afternoon. So we have been discussing about interaction of particles with turbulence, and we'll continue that discussion briefly, whatever the parts are left, and then after that we will discuss about the flow results. Okay. So if you recall, then we discussed that Tu is our momentum relaxation time, and Ly(u) is the time scale of the flow. Okay, and if tu is small compared with the time scale of the flow, then particles will be actually stabilizing the flow, because particles will try to follow the motion, and while following the motion these will consume the energy, turbulent kinetic energy, and ultimately these will result in decrease of the turbulent intensity. On the other hand, if tu is large enough in comparison to the flow time scale, in that case the particles will not be able to follow the flow, and particles will respond slower in comparison to the fluctuations in the flow. In that scenario, what will happen? Flow will take place over the particles, and that will lead to generation of more turbulence. Okay. Likewise, whenever we are talking about the particles, in the previous discussion we assumed that all the particles are of actually solid nature. Okay, but when we are having multi-phase flow, in place of solid we can have fluid particles as well. Okay, so typically if we talk about, say, we have a gaseous bubble present in the liquid, then we know that the gaseous phase is having compressible nature. So because of its compressibility effect, if say pressure in these directions is increasing, it can deform in this type of shape, and when actually there is some reversal of the pressure, then it can occupy this type of shape. So we can see that when gaseous or liquid particles are present within the flow medium, then these particles can have oscillations in their shape. Okay, so say it is changing from this shape to this and then again to this, so these can have this type of oscillations in the shape change. So if we are able to estimate the oscillation frequency of the shape change of these fluid particles, and if I compare it with the natural frequency of the fluid particle, if this ratio of omega m divided by omega n is very small than 1, then the primary effect of the bubble is to increase the effective compressibility. On the other hand, if the reverse situation is there, that frequency of the shape oscillation of bubble is either comparable to natural frequency, or it is more than the natural frequency. In that case, what will be happening? The bubble oscillations will take place at faster pace in comparison to the its natural tendency, and it will try to actually destabilize the flow. Is this point clear? Now, so that is what I have already told you. So we can have some bands of frequency in which flow is less stable and bubbles are therefore destabilizing. Okay. So in general, we have seen that because it's not only the particle relaxation time. In case of fluid particles, along with particle relaxation time, there will be oscillations in the shape of the particles also. Okay. So in general, we can say that when the response time of particles or bubbles, both relaxation time and natural period of volume oscillations, these are short compared with the times associated with the fluid motion, then the particles will be quickly responding to the flow. And what can be done? We can say that particles can be characterized, or the complete flow can be characterized with effective properties such as effective density, viscosity, and compressibility, etc. And in order to characterize the flow, instead of using the characteristics of one particular fluid, we can define the mixture density, mixture viscosity, etc. to characterize the flow. Is this one clear? So let's see. For example, if I assume that I have solid particles present in the fluid, and these solid particles are having, say, volume fraction of alpha. So effective increase in density, or I should say the effective density of the mixture of these solid particles and gas will become equal to 1 plus alpha into rho s by rho g. So this will be the actually effective increase in density. I should say this as multiplying factor with rho g for effective density. Is this one clear? Likewise, if you see in terms of viscosity, then effective viscosity will become 1 plus 2.5 times alpha into viscosity of the gas. So this factor 1 plus 2.5 alpha is the factor for enhancement of viscosity. Is this point clear? Depending upon the volume fraction of solid particles present. Now, if density is increasing by this factor and viscosity is increasing by this factor, we know that Reynolds number will be increasing by, because in Reynolds number definition, density comes in numerator, viscosity comes in denominator. So this particular factor will be able to characterize effective Reynolds number is equal to, say this factor is my k times of Reynolds number for the gases. Okay, is this one clear? And now whatever the flow parameters I need to specify, that I can define based on this effective Reynolds. Okay. And if the response times are comparable or greater than the typical times associated with fluid motion, then particles will not follow the motion of the continuous phase. So if particle is not following the motion of the continuous phase, there will be relative motion in between the dispersed phase and the continuous phase. So once there is relative motion, we cannot make the assumption of the effective property. Okay, means we can take effective properties, but at least flow parameters cannot be effective. Like in previous case, while defining the Reynolds number, I have simply used the multiplication factor for mixture properties, and velocity in both the Reynolds number I considered the same, because particle size was so small that whatever is the velocity of the continuous phase, same will be the velocity of the dispersed phase. Okay. But in scenarios where the relaxation times are comparable or greater, there actually particles will not be able to immediately acquire the velocity of the continuous phase. So it will not be able to sense the fluctuation in continuous flow parameters. So always we will be finding some relative velocity in between the particle and the continuous phase. So because of this, we cannot take this simplified assumption of assuming same velocity and then using the effective properties for characterizing the flow. Is this point clear? The disturbances which are caused by the relative motion typically tend to generate unsteady motions, and these promote instability in the continuous phase, and ultimately we have more generation of turbulence. Okay. Now this is something about averaging. So okay, I will not go into mathematical detail, but let me quickly explain to you about the averaging process. If you recall, while we were discussing about the control volume for defining the multiphase flows, we used one parameter epsilon, which represented the volume of the control volume. Okay, and this volume of the control volume we have selected in such a way so that the finite number of particles of dispersed phase can be accommodated inside a single control volume. Okay, and there only we made one statement. At that time I skipped that statement, that the averages of the properties are not equal to, derivative of the average properties are not equal to average of the derivatives of the properties. Okay, so that is what is given over here. So one of the way for defining some property, some volumetric average of some property of continuous phase, So QC for a continuous phase is defined as 1 by volume of continuous phase into integral of volume of continuous phase into QC d. If I have to define the average of the same property, but not with reference to volume of continuous phase, but with reference to volume of the total volume of the computational, total volume of the control volume, then how we can define, instead of using, I will be using 1 by V and integral of QC, because variation I am only accounting for the continuous phase property. Okay, so that's why, because variation of continuous phase is only considered, so integration should be only over the VC part. Is this one clear? Now, if I multiply by VC and divide by VC, then VC by V will become alpha C, and 1 by VC will be coming over here in the denominator, which will make this average equal to this. So it means that if you are taking the average only over the continuous phase volume, and if you are taking volume of same property for the continuous phase only but with reference to the total control volume, then the average with reference to total control volume will be equal to volume fraction of that particular phase time average of property using the volume of that particular phase. Is this point clear? Now, up to this point it is simple, but after this you can see one important term. What is this? Del QC by del Xi. Okay, so QC is any property of continuous phase. If I write del QC by del Xi, what it means? It means the gradient of QC with reference to position vectors. So it means it is gradient of the QC property. If I define the gradient of the QC and if I take average of this gradient, okay, that can be written in terms of gradient of average of that particular property minus 1 by B into SD, where SD is surface area of the dispersed phase, into QCNI ds. So it means this is coming over here as a correction factor. How this correction factor is coming, I am not going into mathematical definition, but one important point you have to see, that what we have in left hand side. In left hand side we have gradient of property and its average, and in right hand side first term we have average of the property and gradient of the averaged property. Okay, so mathematically how this additional term is coming, that I am not going to define, but what we are able to see, that for a multi-phase flow situation, when we do calculate the gradients, then gradient of the property, average of gradient of the property is not equal to gradient of the average property. Okay, and this additional correction term is coming over here. So basically the order of this additional correction term comes out to be d by epsilon square. Okay, where what is d? D is size of the dispersed phase particle and epsilon is volume of the control volume. So if the ratio of d by epsilon is very small, in that case what will be happening? The control volume will contain finite number of dispersed phase particle within it. Okay, and the magnitude of d by epsilon square will be small. So if your size of control volume is sufficiently large enough to accommodate the finite number of dispersed phase particles, in that case the magnitude of this additional term will be very small and the gradient of property, its average, can be made equal to gradient of the average property. Okay, however, if d by epsilon ratio is large, then these two will not be same. When you do calculate the, so likewise, if this condition is satisfied that d by epsilon is very small than 1, then the time derivative of these properties will also be becoming same if this condition is not satisfied, like d by epsilon is either nearly equal to 1 or greater than 1, in that case this additional correction term has to be taken into account. Okay, so let us just discuss only this much part. Like averaging we can define in different ways. Either I can first define the average of the property for the control volume, and then I can estimate the gradient of that average property, or say derivative with time for that average property, or other way can be that first I calculate the gradient or time derivative of the property, and once I have defined that, then I take its average. Okay, so these are the two different processes, and of course in these two different processes, if d by epsilon is small, then both will be giving the same outcome. If d by epsilon is large, then these two terms will give the different outcomes. Now let us discuss more about flow regime maps. Okay, so typically till this point we have got the idea about the governing equations which are applicable for multi-phase flow. Okay, and we have seen that these governing equations are having different forms. Okay, now depending upon the physical nature of the flow, we have to decide that which type of governing equation we have to choose. Okay, so before choosing the governing equation, we should also know that how my phases are distributed within the system. Unless or until the distribution of the phases is not clear, we cannot select the appropriate governing equations for analyzing our flow situation. For example, if I say that my particles are of very fine size and these are dispersed within the continuous phase, then I can simply make the assumption of what? Homogeneous flow. I can assume that the velocity between the dispersed phase and continuous phase is same, there is no relative velocity, and by just measuring the effective properties, and I can simply use the mixture continuity, mixture momentum and mixture energy equation. Okay, on contrary, if it is clear to me that particles are of larger size and there is significant drift between the two phases which we are considering, then we have to account for individual phase equations, and in the individual phase equations we have to define the interaction terms across the phases. Okay, likewise if we have well separated flow, then most bulk portion of the phases we can solve by using single fluid formulation, and particularly near the interfaces we have to go for the two phase formulation. Okay, so it means that in order to choose the appropriate form of governing equation, we must know how the phases are distributed in a particular system. Okay, now distribution of phases is actually very complex. So flow regime gives the idea about spatial distribution of phases present in the system. Now can you tell me on what parameters this spatial distribution can depend? If you have a circular pipe, then there can be different arrangements of the flow. If you have a rectangular pipe, then there can be different distribution because corner effect will come into picture. Okay, if you have some pipe bend, then something else will happen. If you have horizontal pipe, vertical pipe, inclined pipe, so it means that channel size, cross section, and you can also say channel orientation. So these are some parameters which will be affected. Then what else? It will also depend upon the requirements whether my phase or flow is adiabatic or it's a phase change process. Okay, because if I am having adiabatic situation, then depending upon the rate at which we are supplying flow from the inlet, mostly it should have almost same amount of volume fraction present at different portion of the pipe. Okay, but if I am having phase change process involved, for example in case of flow boiling, then what will happen? At near the inlet of the pipe I will be having less vapor fraction, but as I will be moving away from the leading edge and coming closer to the end of the pipe, there more amount of vapor volume will be generated. Okay, so vapor fraction will be increasing and liquid fraction will be changing along the length of the pipe. Okay, so it means whether my flow is adiabatic or whether it is diabatic. Okay, so heat transfer is involved or it is not involved, depending upon that also distribution can change. Is this one clear? Next important point is, typically if you have a pipe, okay, so say this is my pipe and in this pipe I have to allow two phases to flow. So I can define inlet of the phases in different way. For example, in one case I may have some Y section type inlet where fluid 1 is entering from here, fluid 2 is entering from here. Okay, so while this inlet is there, at this junction I can have crossing velocities and this can create some mixing effect at the junction point. Okay, instead of this I can also have some arrangement where this is my pipe. In this pipe I have, say, some separation plate over here. Above this separation plate one fluid is coming and below this separation plate second fluid is coming. Okay, so in this case both the phases are actually coming with smooth entry. Okay, there can be some scenario where through some center portion I am having one fluid entering and then through the annular portion some other fluid is entering. Okay, so I can have different design of inlets available for the flow. So it means that initially, typically in the initial portion, so as in case of single phase flow, what we have entrance effect, and once we have sufficiently moved away from the inlet portion of the pipe, after that entrance effect becomes negligible and flow is almost fully developed. So it gives similar characteristics irrespective of the design of the intake. So likewise, nature of entrance will influence the distribution of phases typically near the entry portion. Okay, but if we move sufficiently away from the entry portion, then its effect can be less. Is this one clear? It will also depend upon the fluid properties and flow parameters. So for example, if you have one gaseous fluid and one liquid fluid flowing together, then their density and viscosity ratios will be very, very large. On contrary, if you have two liquids jointly flowing inside a single pipe, then the ratios of their density and viscosity will be less. Okay, so accordingly the corresponding magnitude of corresponding forces will be actually changing significantly. At the same point of time, flow parameters like velocity etc. will also be controlling the flow. Now, whenever we talk about single phase flow, then depending upon fluid properties and flow parameters, we have majorly two different types of flows. One will be laminar flow and other will be turbulent flow. Okay, but in case of multi-phase flow, because multiple fluids are associated, so their distribution will be actually different. So depending upon the different distribution and association of the phases, there can be multiple flow regimes present within the system. Okay, so let us try to see what type of flow regimes we typically encounter. So here first we are talking about flow regime map. So flow regime is a particular condition of distribution of the phases, and flow regime map try to combine the multiple combination of flow parameters which results a particular regime, and it also gives the transition boundary from one type of distribution of the phases to other type of distribution of phases. So it means it also defines the transition boundary from one regime to another. Okay. So in this flow regime map, first we will be discussing only for the horizontal pipe flow. So orientation we have fixed that our pipe is horizontal. Okay. And this particular flow regime map, what we are showing over here, it is for air water and the size of pipe is 5.1 centimeter. So diameter of the pipe is 5.1 centimeter. Because I already told you that flow regime is something which depend upon the distribution of the phases. So as it is depending upon distribution of phases, it means whatever this analysis we are doing, this is based on the visualization of the flow. That is first point. Second important point is, it is also known to us that the nature of the entrance influences the flow. Okay, the way we are allowing two fluids to come, it will be influencing the distribution of the phases present in the pipe. So while we are trying to characterize the flow regime map, we should choose a location sufficiently away from the inlet of the pipe, so that the effect of entrance or the nature of the entrance of the pipe should not affect much the flow. Is this point clear? So that's why while characterizing this flow regimes based on the visualization, we should move sufficiently away from the inlet of the pipe. Okay. So here you can see in this flow regime map, what I have plotted on abscissa is mass flux of water. So mass flux is GL, and we know what is GL? Rho L into GL. Okay. And here it is mass flux of air, which will be rho G into G. Is this one clear? So these are nothing but mass flow rate of liquid per unit total area of the cross-sectional area of the pipe, and mass flow rate of gas per unit cross-sectional area of pipe. Okay. So now let's first come to the scenario. In this scenario, my mass flux of water is very less. Okay, so water mass flux is very less, and slowly I am increasing the mass flux of the gas. So what happens in a pipe if you allow water to flow inside a pipe, but flow rate of water is very less? What happens? Typically, if you have an empty pipe, and in that pipe, whenever you switch on the pump and allow water to flow in the pipe, if mass flow rate of water is, or volumetric flow rate of water is less, what happens? Typically, we see that the water fills some portion of the pipe. It does not fill the complete cross section of the pipe, and above that portion of pipe there is air present. Okay. So likewise, in case of stratified flow, my mass flow rate of the liquid is so small that it is not able to displace the gaseous phase which is coming with these velocities. Okay. So that's why the liquid phase is partially filling the pipe, and because of its heavier density, because of its high density, it is a heavy material, and if gravity is acting in this direction, because we are considering the case of a horizontal pipe, liquid will stay at the bottom and gas will be staying in the upper portion of the tube. Is this one clear? And if you look it from the cross section, you will be finding half of the portion is filled with liquid and half of the portion is filled with the gas. So if you know this, you can easily do calculations for half this much sector of pipe using the liquid properties, and for this much sector of pipe using the gaseous properties, and then at the interface you can apply your interfacial conditions. Okay. Whenever your flow rate of liquid and gas are small, in this scenario we will be finding that the relative velocity over the liquid and gas phase is not much, and the interface between them will almost stay flat. Okay, so this type of situation is called as stratified flow situation. Now if you keep the same values of liquid velocity but increase the gaseous mass flow rate, what will happen? Relative motion will come between the two. Once relative motion is coming between the two, we will be finding that interfacial shear will come into play. Okay, and because of the interfacial shear, we will find that some wavy patterns or disturbance waves will start appearing on the free surface. You can assume a lake of water. Okay, so when you see that there is in a lake of stationary water or pond of stationary water, if there is no surrounding air disturbance, surrounding air is almost still, we find that interface of the lake is flat and almost it appears like a stagnant and fully flat. But when you see that the wind start blowing over it, then what happens? We find some ripples forming over the water surface. So likewise, whenever you have significant relative motion between the liquid and the gaseous phase, then this wavy pattern will start appearing and we call this as wavy flow. Okay, so liquid properties were almost the same, that liquid is not able to displace the gas, but what we did increase the gaseous flow rate. Okay, and upon increasing the gaseous flow rate, we have seen that wavy stratified flow has come into picture. Is this point clear? Now what will happen if I keep the gas flow rate as small and I start increasing the liquid flow rate? What will happen? Liquid will try to fill in the more portion of the pipe. So once liquid is filling more portion of the pipe, it will try to displace the gaseous phase. Okay. Once it is displacing the gaseous phase, we will be finding that gas will be coming in the form of intermittent bubbles. So these small gas bubbles will be appearing on the top portion of the pipe. Why top portion of the pipe? Because of gravity, lighter phase will be collected at the top. And liquid flow rate has become sufficiently high. So I have gone from here to here. Liquid flow rate has become sufficiently high that it can displace the gas and fill almost the complete portion of the pipe. Okay, but from the back we are also supplying gas at certain flow rate, so that gas will be actually co-flowing with the liquid in the form of small bubbles. So this type of situation is called as bubbly flow situation. Is this point clear? Now if you see that you are keeping the liquid flow rate almost the same but slowly started increasing the gas flow rate, what will happen? Whatever the small bubbles were coming, instead of that now larger sized bubbles will come. Okay, or if say multiple bubbles are coming, then the frequency of these bubbles will increase. More number of bubbles will be coming, and more number of bubbles, when these will be merging with each other, these will be forming larger sized gaseous bubbles. Is this one clear? And these larger sized gas bubbles will be almost touching the top portion of the pipe, and these will be co-flowing with the liquid. So this type of flow is called as plug flow. Is this one clear? And you will find that further increase of the gaseous flow rate, keeping the same liquid flow rate, a situation will come when what will happen? These gas bubbles, their frequency will be so high that these will be merging together with each other, and these will form big gaseous chunks which are called as sludge. Okay, so we will be entering into the sludge flow design. Okay, now at very high gaseous flow rate, what will happen? At very high gaseous flow rate, gas will try to displace the liquid, okay, and it will try to enter towards the center portion of the liquid. Is this one clear? Because if you have to supply very high amount of mass flux of the gas, what will happen? If gas stays close to the wall, then what will happen? Wall is stationary, gas velocity will be very high. So this will be becoming the zone of high shear. But being liquid as high density fluid, if you are achieving almost the comparable mass flow rate, the corresponding volume flow rate for liquid will be less. So close to the wall, liquid will be having less velocity. Is this point clear or not? Say you have two situations. You have a pipe. In that pipe, at some mass flow rate, gas is flowing. In the identical pipe, at almost the comparable mass flow rate, liquid is flowing, which will be having high volumetric flow rate if mass flow rate is same in both cases. Density of liquid is more, so volumetric flow rate of liquid will be less and volumetric flow rate of gas will be high. So if volumetric flow rate of gas will be high, it means near the wall, gas will be having more shear in comparison to the liquid. Okay, and typically the characteristics of the fluids is that they try to adjust the situation of low shear or minimum possible shear. Okay, so in this way they will adjust in such a way that the fast moving gaseous phase will get accumulated near the core and the slow moving liquid phase will get accumulated near the outer phase.
So no slip नहीं आएगा, no slip condition.
Yes, no slip is there, but ultimately because of the no slip, what will happen? After no slip, if this is the velocity profile for the liquid, then what will be velocity profile for gas to meet the same flow rate? Sorry, to meet the same mass flow rate. It will be this high. Now, in which case shear will be more? Say this is shear profile for liquid, this will be shear profile for gas. Okay, so the substance which is giving the less shear, there actually your system will try to equilibrate, because in that scenario system has to invest less energy. Okay, so typically our system try to equilibrate to the scenario where it has to invest less amount of energy. So ultimately we will be finding that the high shear portion will be moving to the center and less shear portion will be actually adjacent to the wall in order to balance the overall nature of the process. Okay. So in this way we will be finding that gas is coming towards the center in the form of fine bubbles, or sorry, in the form of continuous phase of gas is at the center. Outside there is a liquid film, and in this gaseous phase small droplets of the liquid are also actually present. Is this point clear? And if you look from the cross section wise, cross sectionally you will find some situation like this, where this is your liquid, this is gas, and in the gas there are some liquid droplets present. Okay, but one interesting characteristic, you can see that the liquid film here will be thicker and liquid film at the top will be thinner. So this will be because of the presence of the gravitational field. Okay, gravity will try to keep the lighter phase more towards the top portion. Okay, so this type of situation in which one phase has acquired the outer periphery of the pipe and other phase has accumulated within the pipe, that flow is called as annular flow. Is this point clear? And typically at excessively high liquid flow rates, you will be finding that gaseous bubbles will be coming in the form of dispersed, very fine dispersed bubbles present in the continuous liquid phase. Okay, and your phase will be entering into the dispersed phase result. Okay, now one interesting point you can see, what is this hatched portion over here? Yes, so hatched portion is representing the zone of transition from one particular phase to other. Now, it is not given in the form of a sharp boundary, but it is given in the form of significant band. Why significant band? Because this is the portion where your flow is in the transition stage. Transition stage means if any instability grow at this particular stage, then flow can either enter into the wavy regime, or if the instability diminishes, then it can continue staying in the stratified. Okay, so whenever you define the separation from one phase to another phase, it is extremely difficult to find single set of conditions which represent sharp transition from one phase to other phase. Instead of that, we will be having a significant set of parameters through which flow can adjust to any of the boundaries. So that's why this transition band is represented with the thicker joint. Okay, and this is based on the experimental results. On contrary, if you see, along with this, I have also given a black colored boundary. So can you tell me what is this black colored line? Once we theoretically analyze the flow using the governing equations what we have discussed, this black colored boundary gives the theoretical transition limit or theoretical boundary between the two phases. Okay, so when we solve the governing equations, the solution of governing equations will be giving us the unique solution. It will not give some range of parameters. That's why theoretically we will be having clear distinction. Okay, so typically when we study the transition from stratified to wavy regime or annular regime, what we do, we consider that these two fluids are co-flowing together, and at this interface, if I artificially or mathematically introduce some perturbation, okay, if the set of conditions for which this perturbation will be diminishing, okay, it will not grow with time, these conditions will stay in the stratified flow regime, but for the set of velocities and the flow parameters in which this mathematically introduced perturbation, if it grows its amplitude in significantly, in that case it means our transition from stratified to wavy or other regimes will be happening. Okay, so typically the theoretical analysis which gives the transition from stratified to wavy regime based on the difference of relative velocities across the interface, that is called as Kelvin-Helmholtz instability. Okay, so if you have two different phases and the velocities in the gas and the liquid, these are different, then depending upon the difference of velocity, whatever instability grows at the interface, that instability we call as Kelvin-Helmholtz instability. Okay, and this Kelvin-Helmholtz instability will be giving me some limit, that below this limit if I take velocities, then any perturbation which is growing at the interface, that will be staying, that will be diminishing. It means flow will be staying in the stratified regime. But if any perturbation is going beyond this boundary, then that perturbation will grow, and because of the growth of that perturbation, the flow can enter either into the bubbly or the slug flow regime. Is this point clear? Like in case of laminar and turbulent flow, what we study for a pipe flow that Reynolds number of 2300 is a critical limit at which flow starts transitioning towards the turbulent flow. What it means? It means that if any perturbation will be present in your pipe flow and your value of the Reynolds number for the pipe flow is less than 2300, then that perturbation will be dying down in the downstream direction. But if your Reynolds number is greater than 2300, then that perturbation will amplify, and because of the amplification of that perturbation, finally we will be getting vortices generating into our flow, and ultimately the flow will be attempting the turbulent region. Okay. Likewise, in Kelvin-Helmholtz instability, now instead of any perturbation in the velocity field of the flow, here we can have perturbation at the interface. Okay, so in the interface shape. So if that interface shape is diminishing, the perturbation on the interface shape is diminishing, it means interface will stay flat in the downstream direction. But if this perturbation which is introduced at this point, if it grows in amplitude, then ultimately it will become a slug-like situation. Is this point clear? So this black colored boundary is something which gives the theoretical transition from one flow regime to the other flow regime, and this is typically the limit of or the theoretical condition for the flow parameters at which any perturbation of the interface will be growing in such a way so that it will lead to change in flow regime in the downstream. Is this point clear? Now, because it is, of course, when we go into the practical scenarios, it is not always precisely, it will not always be possible to precisely control the flow, as well as when we are doing Kelvin-Helmholtz instability analysis, we are making assumption that in one particular regime the flow is purely horizontal, but it may happen that flow may not be purely horizontal. There can be some component which is in oriented because of the entry effect or other experimental uncertainties. Okay, so because of which whenever we do experimentally calculate the transition boundaries, then we do not get the unique value, but we have some transition band actually. Is this one clear? Okay, now the way I discussed the flow regime map, now another flow regime map is given for air water mixture, and this is typically for horizontal pipe of 2.5 centimeter diameter, which is at, and the flow is allowed at 25 degrees Celsius and 1 bar pressure. Okay, and in this scenario also you can see almost the flow transition limit and flow parameters are almost the uh, going through the same set of regimes what we observed in the previous case. That this is one good comparison. Here you can see the multiple transition boundaries are actually shown. Okay, so these multiple transition boundaries are corresponding to various pipe diameters. For example, the dotted line is for 1.25 centimeters. So this is your dotted line. So this dotted line is showing the theoretical limit of transition from stratified to wavy flow for 1.25 centimeter pipe. Then this is the solid line which is for 5 centimeter diameter pipe, and this dash dot line, sorry, this solid line is for 2.5 centimeter, and dash dot line is for this particular is for 5 centimeter, and for 30 centimeter this dashed line. Okay, so
in this graph, plug flow कितनी है इसमें?
which one, this particular one?
Uh,
In both. Okay, so basically because all these flow regime maps are given by different researchers. Okay, for example, here you can see this was from this work, this is from this work, and this is from some other work. So what has happened, typically the flow regime maps which have come long back, these are from the visualization studies, and mostly these are from the nomenclatures which are used by actually different people. So it may happen that some person who has seen that multiple bubbles are merging together and forming a larger sized bubble, he might have given some name as plug flow. But what this guy has done, instead of plug, this he has given the name as elongated bubble flow. It means bubbles are elongated along the floor. So these are based on the visualization. So different people have used their different nomenclature. So over here our interest should be to specifically see what is the distribution of the phases. Okay, to determine the conditions corresponding to distribution of phases rather than their name. Okay, so name you can find some differences because all these observations are based on the nomenclature and the flow visualization observed by different people.
Sir, practically, like how can, let's say liquid is flowing through a pipe, then how can we introduce the air in it?
Because
Like how people introduce air in the pipe? How
yes, so practically when one has to do, the arrangement will be something like this. Say this is your pipe. In this pipe you can have multiple arrangement. One of the possibilities I am showing over here. Say you have designed your intake something like this. Now this particular portion of pipe you have connected to a pump which is taking water, and this particular portion of pipe you have connected to a blower which is taking air from the atmosphere. Now you see, so from here water will be coming from the top. If you simultaneously on the pump and the blower, what will happen? From here water will come, from here air will come. Is this one clear? So we can design the intake arrangement and the circuit in such a way so that multiple fluids can simultaneously enter inside a single pipe.
Sir, these are the graph by visualization or any software is also used for.
These initial observations are, because you see these are from 1974. Okay, so this is the period when computational fluid dynamics was just at the very initial phase. Okay, so if you see the finite volume method and maximum growth of the development of solution methods for single phase flow, numerical solution of single phase flow fluids have started somewhere close to 1970s, and by the end of 1975 we were having algorithms only available for single phase flow. By that time the solution, this computational analysis of multi-phase flow was not possible. But if you now presently refer some paper from say 2015 or 2020, there you may find that some people have plotted the flow regime map based on the numerical simulations, because now the simulation techniques uh, which can solve the multi-phase flow problem or determine the solution of multi-phase flow problem using computational fluid dynamics are actually well developed. Okay, so this is actually a growing, evolving field. For example, in single phase flow, most of the things people have done before. So nowadays whatever is there in your textbook, that is kind of, for certain areas you can see things are saturated, though things never saturate, something will be actually keep on developing. But for multi-phase flow, presently in majority of the books, whatever flow regime maps you will be finding at present, these will be majorly based on the pure theoretical analysis for regime boundaries and the experimental observations. However, the recent papers, particularly after 2010 or 2015 onwards, if you see, there we have the significant developments in the computational solvers for multi-phase flow problems, and you will be able to see flow regime maps based on the numerical simulations as well. Okay. So here, like what you can see, that whenever you are increasing the size of the pipe, then transition from 1.25 centimeter to 30 centimeter diameter, you see this much difference has come. Okay, so it means that the defining universal boundaries is actually quite challenging. So situations are very much specific to the physical phenomenon which we are actually taking into account. Is this point clear? Now, these are flow regimes for slurry. So already we know that for slurry, whenever the particle sizes are small, say somewhere close to 5 to 15 micrometers, and volume fraction of particles is low and velocities are sufficiently high, then we will be finding there will not be any particle-particle interactions and particles will be almost suspended in the flow, which is called as homogeneous flow. And when we see that particle sizes are somewhere close to 30 micrometer and slightly the volume fraction of the particles is increased, some of the particles will start settling at the bottom having non-uniform concentration profile, and this type of flow is called as heterogeneous flow. Okay, if we further increase the particle size and volume fraction or decrease the continuous phase velocity, or we decrease the continuous phase velocity, then what will happen? The particle will start settling at the bottom, and at the bottom this bed will also be sliding over the pipe surface. So this is a moving bed scenario. And when we are having most of the settling and in the top mostly fluid is having only continuous phase present and the bed becomes static, so this will be a situation of blockage of the pipe or slug. Okay. Okay, maybe about gas solid regimes we will discuss in the next class.